Welcome everyone. We are thrilled to have with us today Pritish Kakkar, a visionary in the fields of 3D graphics, AI, and machine learning, currently shaping the future of technology at Adobe. With over 15 years of experience, Pritish combines deep technical expertise with a passion for mentoring and community building. Whether you are seeking to understand complex graphic pipelines or want to explore the intersection of AI and creative tech, this session is for you. So, expert, approachable insights, practical knowledge, and a chance to ask your burning questions live. Please join me in giving a warm welcome to Pritish Kakkar. Hello, sir.
Hello, thanks for the introduction. Let me try to see if I can, because this is a new tool, let me try to see if I can share my slides. Can you see the slides?
Yeah, it's visible.
Okay, and if I move the slides, is it working properly? Is
Oh,
it
yeah.
moving?
No, no, no.
No?
That's not. Yeah.
Okay, let me see what we can do here. Yeah, I'm not used to this tool actually, so let me, okay, let's see. Uh, Okay, let's do this way. It might be easier. Okay, hopefully this is better, right?
Yeah.
Okay, cool.
It's working.
Uh, okay, let's get started. So I'm going to give a little bit of introduction into how you can build a career in computer graphics and vision. I'm going to talk about what are the skills and techniques and how the AI is also changing the computer graphics and vision field as well. Let's get started. I have about 15 plus years of experience in 3D graphics, rendering engines, and physical based rendering. I'm author of the Modern Vulkan Cookbook. I had previously worked at Microsoft, MathWorks, John Deere Stryker. I've been, working at various other companies on ray tracing, rasterization. I will keep this short, but I will get to the main agenda. We are going to talk about introduction to what is computer graphics and computer vision. We're going to talk about various libraries, and I'm going to skip some slides depending upon the time that I will have. Um, so we will try to cover what we can, but we will also skip something that I feel is not very, relevant. Okay, let's get started. So, as a first thing, talk about what is computer graphics. So, the idea with the computer graphics is it's a field where you are visualizing, like you want to generate images from some synthetic scenes. So, let's say you create a spatial information. You say, okay, this is a 3D object. This is a shape of this 3D object. You can define it. There are various ways to represent a 3D object, but a very common way would be you have certain vertices and you say how those are connected to each other. So you have this object which is called meshes, right? And then you have light in the scene. So you're trying to create this kind of scene to represent some kind of a real world thing. So for example, if you have a room, you try to go to Blender and to try to mimic what is in your room, and then you create a scene for your room, and then you would be able to now render it from any camera direction. And that's pretty much what the field of computer graphics on high level is. You have synthetic data that you are going to have to change it, provide the information, and then you are producing a 2D image. And this would of course, in a scene you could have animation, modeling, visualization. So those are the kind of things you will do. Let's talk about kind of, on the high level types of computer graphics, right? So you could have very 2D computer graphics kind of thing. So computer graphics is a broad category, and what I described before was actually more on the 3D side, which is what I work and like to work on. But computer graphics is a very broad category, right? So for example, if you're doing 2D graphics, you're focusing on a flat image, you're making some changes into it, let's say making it blurry, making a cartoon shape, adding some kind of basic visualization. That's pretty much what would be 2D graphics. 3D graphics, like I said before, would involve like lighting, perspective, all the 3D things that you kind of don't really think in real world, because as a humans we all see everything in 3D, right? So it's very natural for us to see a shadow and really not worry about how this shadow produced, because we have evolved and we have lived in this world, and that's how our human brain has got a sense of depth. For example, we don't really think about it, but a lot of this is very very core mathematics and a lot of hard problems to solve to be able to represent and create like a realistic 2D image out of a 3D data, if I give you the 3D data. And that's pretty much what is 3D graphics. Then there is another field or another sub area, I would say, which is called I would not really call it like a separate thing, but it's more like a tangential to 2D or 3D graphics. You could represent your data as a vector or raster, right? So, for example, if you are using vector graphics, you don't really draw pixel values. You don't have you don't say, I have a 10 by 10 image and I'm going to change the pixel value. What you say is, I have this line that goes from this location to this location, and then it connects like this. And then maybe I have a triangle, maybe I have a sphere. You basically draw shapes and path, and that's very much, if you're using like things like Adobe Illustrator or any kind of SVG editor, that's what you are doing. Basically, you are doing vector graphics. While if you are just simply doing any pixel kind of manipulation, where every particular, like let's say you are saving into a PNG, JPEG, or any kind of pixel manipulation you are doing, you are basically doing a raster graphics. Computer graphics has broad, applications. You will find a lot of application of computer graphics in movies, video games, animation, effects. VR is another field which is booming, and is a lot of AR VR devices are used for interactive experiences, for training, education, and gaming. So those are the other things. And then of course, if you want to simulate complex environments for training, like aviation, military, or any kind of those kind of trainings, is another thing where graphics becomes important. Graphics, another very core use of a lot of computer graphics skills is into medical software. Like if you're visualizing CT scans, MRI scans, and a lot of software that is used for surgical or diagnostics planning, those kind of things used by surgeons, actually has a lot of programmers who has done some kind of computer graphics into it. So and then of course, if you are doing CAD to create models that you're going to do, or any kind of visualization for buildings and be able to architecture building, for example, Autodesk has software like Revit and stuff like that. That's basically pretty much architecture software. All of that is also requires a lot of skills in computer graphics. Common skills that are required in computer graphics, like if you want to be a graphics engineer, you would need to understand a lot of libraries like OpenGL, Virtual. These are not really libraries, these are more like API specifications. So you will need to learn how to use these APIs, and libraries that works with these APIs to build something which is called like a game or rendering engines. You will need to understand how GPUs works, how shader programming is done. You will also need some foundation, I would say, at least to begin with, in linear algebra, calculus, and geometry, transformation, projections, lighting, and things like that. Again, you don't have to know everything in this area, specifically the mathematics part of it, but it's good to have um, at least some basic understanding of it. And as you move along, like once you start doing more graphics stuff, either as a part of your hobbies or some kind of job, you will start getting good in it automatically. You will start reading more blogs on it, and you should start keep looking into these kind of concepts, specifically the mathematical concepts, because they are used. And sometimes when you are working on a project, specifically in an industry, you might have deadlines, so it might not be possible at that point to read or review all your mathematical fundamentals. So you would pretty much at that point of time try to get things done. So it's a good idea when you have time and bandwidth to brush up these concepts. And most of these are not like like it's not like postdoc or PhD level mathematics. It's pretty graduate level mathematics, and most of us has already done this in our past. We just have to review and keep a track of things that we and try to remember what we done previously. Then there is another very interesting field. A lot of artists, they need to do like visual composition of different images, different 3D geometry, how to create them, like modeling, for example, environment design. So you should get proficient in tools like Blender, Maya, ZBrush. There are multiple tools. There is a lot of Adobe Substance tools that you could get good in, and they are used like Adobe Substance Designer, Painter, and stuff like that. Uh, Another very interesting field is what I call is a technical artist. So the idea with the technical artist is it's a you need some kind of skills in programming also, but you also need some kind of artist skills. So you need to understand a lot of details about color theory, lighting, how to write a how to create a particular model. But at the same time, you also need some programming, because not every tool will work for everything you need to do. And you so having that combination really makes you very good. Like if you have some Python code you can write custom script, but you also have a very good math background, and you have also very good, let's say, artist understanding of things and how it would be used for the domain that you're working upon. For example, in gaming it would be different, in VFX it would be different versus, let's say, CAD one. But if you have a good understanding, you could write like scripts, custom shaders to do some mathematics things, and get the things done. So those are the very high level fields and the skills that are required, that in different areas that you can develop over time. Now let's talk about some key areas in computer graphics, or 3D graphics, not really computer graphics, but more on the 3D side. So one of the ideas is rasterization. So the idea with rasterization is you have like this 3D world, right? You have 3D models. We are going to convert it into 2D image. At the end of the day, that's the goal, right? You have a certain 3D data. You're looking at from a certain direction, but you're converting it into a 2D image. But the idea is you want to make sure you get it as much close to reality as possible. Like if I took a picture of some room from a certain angle, and the same room was modeled in the Blender, when I try to render the same room from the same angle, it should uh, ideally it should match one to one with the physical reality, but that's very hard. But in rasterization is a technique where we lose some physical accuracy over speed. We basically prefer to do it fast, because this is something that needs to be used in games or real time applications or interactive graphics. And that's why speed is more preferred. So we do some kind of hacking. Sometimes we try to make things resemble as close as possible, but we don't try to make it absolutely accurate to how the reality and the physical world works. So a lot of algorithms and rasterization techniques are not designed and not inspired by how the real or how the actual physical world work. They are kind of hacks trying to simulate how the physical world would do if, like, think about this as, like, let's say you do some kind of statistical analysis on something, and you are trying to use some kind of statistics to figure those data out during that. But that way you gain speed instead of doing it over the being physically accurate. Then there is a array or path tracing techniques, and that's what we do. That's what is used in like VFX or gay or like movies, like from Pixar, from Disney, from DreamWorks. So a lot of these um, they have engines called path or ray tracer. The idea there is you want to simulate how the light behaves in the real world. So if you imagine what happens in real world is you have this camera, and at in the real world there is some light sources. The light is bouncing between different objects, it's getting reflected, and eventually some light is all the light paths are continuously getting bouncing around, continuously being reflected. But as they are being bouncing as they are hitting different surfaces, they are also losing some energy, because some of the energy would be consumed by the surface that it hits, right? And eventually some of these bounces that has happened would make it to the camera, right? And that's what the camera image would see. So that's what we do in ray tracing. So we still have 3D world, but we are now not only trying to just do hacks to simulate and create this 3D image. We are really trying to do trying to do as if things works in real world, which is like for each pixel we will throw a ray. We will see where the ray hits, and then we will try to do what happens on this surface, how much gets consumed. Is it gonna be, and there is concepts like index of refraction, what would happen, like in like the concepts, all the physics concept that you have read in your school time, you would be using this, because if a ray is going from one medium to another, for example from air to water, it's gonna basically, its path is gonna get changed based on the index of refraction. So all of those concepts would come into the play, and those are very important, and you have to do it exactly how the physics, how our physics tells us all the properties of the light that we have understood to produce the realistic images, right? We want to produce photorealistic image, and photorealistic here means as accurate as possible to the reality, almost so accurate that it's almost difficult to distinguish between whether it was a real picture taken from a camera or a picture that was just rendered through computer imaging. So this is high level on ray path tracing. And then we have, of course, different techniques for real-time rendering. The rasterization and path tracing are like the high-level techniques that are used, but there's terminologies like real-time rendering, which does not necessarily means that it's going to use rasterization, but most of the time it means that for real time you would be using rasterization. But as the GPUs are evolving, sometime even for real time, there are parts of ray tracing that can be used along with rasterization, like in some parts of that. It's not totally replacing rasterization, but parts of the rasterizations can be replaced. So these are the some of the terms you will hear. Then there is something called global illumination. So the idea with the global illumination is so one is called direct illumination. Think about direct illumination as I shoot a ray from camera's pixel. Let's say I'm looking at a camera which is showing me 250 by 250 image. For each pixel I shoot a ray, whichever surface it hits first, that becomes my color. So in this case, it's called direct illumination, because directly you are getting whatever the light is gonna happen, or whatever surface it's gonna hit, but then means all the indirect effects that you would see, because other rays coming from other direction of other lighting sources would hit that particular object that your ray from the camera hit. You miss that. So global illumination is a term that means that you are not going to only take into account the direct part, but also the indirect lighting part to get the right lighting or realistic scene lighting. And physical based rendering means it needs to resemble how the physical world works. So we want to have to simulate properties of the materials, because in the world we will have different materials, right? We could have like gold would have a different properties, plastic would have a different properties, glass would have a different properties, something more metallic would have a different properties. So we want to be able to define some kind of system so that we can say, okay, if you want to create a glass, these are the properties you want to set. Okay, so and to create, and then of course that's how you will be able to get the physical base system. And then there is terms you will hear, like, and these are only few terms, right? You might hear more terms that I might not be able to put it in slide, or it just didn't occur to me. But level of detail is like, in computer graphics, specifically in real time, you want to be able to run things fast. So it's pointless to render something at the same resolution if it's very very far away, right? So think about a 3D model which was very very highly detailed, like let's say a dragon. When it's very close to you, you do want all the look and feel of it, right? All the details. But let's say if it's too far from it that it's going to render into only 10 pixels, then you don't want to use all the data that was available on Dragon, right? So you want to only take the data. You want to basically minimize the data. So as you are viewing the object that are far away, you get things which are at a different resolution, and that's called level of details. Let's talk about computer vision a little bit. So, so in computer graphics, we said we have you know, uh, 2D, a 3D world, and we were going to 2D images, right? So computer vision is the opposite of that, you can think. At least the one I'm talking about. Again, computer vision also have a broad. It's a broad area. It does not mean one thing, but you could interpret it as a something where you are understanding visual information, or you have a set of 2D images and you're going to 3D, world basically from 2D images. Some of the, again, terms you will see is image classification. You might have like face tagging, some kind of disease diagnostic. So you will see some like TensorFlow and PyTorch are common technologies. You will see these already have these algorithms to be able to train and then classify the images. Object detection, tracking, image segmentation, AR, guest recognition, and then 3D reconstruction, like I was talking to you before. Like it's basically inverse of what graphics rendering does. So you can think about inverse rendering as basically 3D computer vision or 3D reconstruction, right? And then we have SLAM, where you are trying to understand AR VR experience, how the autonomous robotics works, how the drone works, and some other things. I'm just going to skip this and move to some more interesting stuff. Okay, let's talk about various industries that you can you would be using some of these skills. So gaming industry is one industry, of course, where you would have all of these skills used for real-time rendering, visual effects, immersive application, world building, physics, any kind of physics engine development, or using physics to do stuff is a lot of that kind of work is done in gaming industry. AR VR is getting adopted in a lot of industries, so a lot of work in AR VR would be required. Automotive and autonomous driving specifically needs a lot of graphics and rendering engineers and computer vision engineers, because a lot of this work is simulating for real world scenario. For a lot of these companies like Tesla and other companies are trying to use some game engines, whether they build it in house or using off the shelf like the Unreal ones, to be able to simulate stuff and then train their data set. And then of course, for them, it's not as simple as just using the synthetic data that is being produced through Unreal, right? They are also have to use some real world data and see how well the synthetic data is working, what changes they need in synthetic data. So those kind of things. Healthcare is another area where, of course, these areas, like I said, for visualization of CTMR and a lot of other things are required. Uh, let's talk about architectural and real estate. Like if you have a website like Zillow or any of those websites, you can 3D view of the houses and stuff like that. You can even use AR applications to view 3D models as things you would look for. Education, of course, for data visualization in general. You will see social media also now these days have these AR effects, right? So all of those have graphics application at the end of the day. Let's talk about some of the key concepts in computer graphics. So, um, so one of the very important thing to understand when you are learning to become a graphics engineer or rendering engineer is what we call shaders. So shaders, think about shader as like these like a C program. I mean, it's not exactly C though. It's a subset of C, you can imagine. But the languages doesn't matters, and yeah, those details would not matter. But the idea is you have some way of programming GPU by writing some code, and then these small programs can run on GPU. And of course, you could ask me why would we not just use C++ or Python or something like that? Because GPU's architectures are totally different than CPU architecture. So the GPU needs a different kind of programming languages. That's why CUDA exists, for example. It's so think about it similar to CUDA, but more tied to your graphics pipeline. Instead of CUDA is more like doing general purpose GPU programming. So you would use these shaders to control effects like lighting, shadows, surface properties. And then the shaders comes in different types. You will have vertex shader, pixel shader, compute shader. I will not really go into detail of these, but if you're interested, you should be able to find a lot of information about these kind of concepts online. I just wanted to give a high level overview at this point. Then you of course have textures, which is like, so think about them as images, but think about an image that is wrapped around a 3D model. So, for example, if I give you a sphere and I give you the, a printout of image of the world map, and I say go wrap it on this sphere. Think about that. So sphere is your 3D model, and this texture is your, printout of that global or globe map that you basically are going to wrap on your 3D model. And of course, there is more to that. I'm making it simple, but for explanation. But of course, there is more to that, right? Like textures can come in different types. You could have normal map, bump map, environment reflection maps. So a lot of different kind of things. Again, I encourage you to read if this is something interesting to you. It's a wide area, so explaining everything in a small presentation is difficult. Meshes is another idea basically. So in 3D world, we want to be able to represent objects by using some kind of concepts, right? So mesh is a way of representing that. So mesh is just a collection of vertices and edges and faces, and that's telling you how this 3D object. So think about basically triangles that are connected to each other, and eventually they give you this 3D object look, right? And then you have rendering pipeline, which is basically different stages of your rendering engine and how it works, and what pipeline processes what part. Some of the key concepts in computer vision area is you want to do something like feature extraction, like you want to be able to describe edges, corners in a texture. You want to be able to do some kind of object recognition and matching. You want to write maybe some kind of convolutions, kernels, like convolution neural networks. You want to be able to do some kind of image classification using some of these. You have, of course, SLAM, which is localization and mapping, which is, of course, used in robotics, AR, VR to make sure, a lot of these concepts. And then, of course, set of point clouds that are created using sensors like LiDAR. You might have heard about some of the AI trends in graphics. For example, a lot of these models like generative adversarial networks or diffusion models like stable diffusions, they can create realistic images from text, for example, or from giving them an image. It could even create like 3D objects sometimes. All of these are some of the interesting areas that are coming up in graphics. There is another concept called neural rendering, which is basically how to use neural networks to do, let's say, upsampling or those kind of ideas. Then, of course, there is a procedural content creation, like you want to use automatically AI algorithms to say, okay, I want to create a texture of grass, or I want to create a texture of a terrain that represents some bumps in it, right? So you can use AI to create like a lot of modeling can be done using AI. Uh, there is another very interesting thing called neural radiance field. Also, parallel thing is called Gaussian splat, where basically you're using, instead of using 3D representation using meshes, texture, and everything, you are representing them using some kind of volume and a neural network that was trained on your particular scene. So this is another area I would encourage you guys to look into. Very interesting stuff going into AI, specifically into 3D graphic space. Look into NERF, neural radiance fields, and Gaussian splats. Uh, I'm gonna skip this. Okay. So, like I said, some of the important roles that you will find in companies would be, of course, graphics engineer, like myself, where we focus on rendering and low level. You probably need skills in C++, some GPU, some shader programming. Uh, Computer vision engineer would be another one where you need skills in PyTorch and similar frameworks. You need to understand a lot of images, image processing, and those kind of details. Also, you could also be someone like a 3D modeler who could create 3D assets. You could look into being a technical artist, which is another interesting area that I encouraged or told you about in some of the previous slides. And of course, you could be AR VR developers who are using some of these engines or vision libraries that were developed by some of these graphics and vision engineers. Most of the times, if you're a graphics or a vision engineer, your role is very much like a back end kind of thing where you are developing the infrastructure, and then the AR VR developer is pretty much using that to develop an application. So you're not always front facing on the app side, unless you are in a very very small company where everyone is trying to do everything. So, like I said before, there is a lot of industries like gaming, simulation, autonomous driving, CAD, medical. So here is another interesting slide where I wanted to show various different use cases of computer graphics, right? So when you watch movie like Jurassic Park that came in 1993, you will see this realistic things, and this is not just, I would say, computer graphics only. It's part of like 3D graphics. Part of this is 2D graphics. Part of this is a lot of very smart creative artists trying to figure out how to merge images together, how to compose things together, right? Like how to put this dinosaurs from 3D thing to into an image, and then how to merge it with this image that is real captured and make sure everything look very realistic and shadows are right. So you can imagine this was state in 1993. So in 1993, when Jurassic Park came in, all of this was computer modeled and then merged with the real world. So a lot of these companies, VFX companies that makes these movies, kind of do have a lot of advanced computer graphics engineers and skill set that they need. Okay. Then you have like product visualization. Here is another, character named column from this series, where you want to create this virtual character, but you want to model it as close to as how the human would do, right? So then you have this motion capture suit where you're tracking almost every part of or every joint of your, or even more than every joint of your body, and that way you are able to simulate all the joints exactly and move all the joints exactly in the computer. So the real actor is doing the acting, but in the computer, the simulated character is exactly behaving as the real character is saying. So his face expression, his body's texture, his body movement is very much replicated that way. This technology has evolved considerably. It used to be very much like this tracker based, where you have to add multiple trackers on your stuff, but not anymore. I mean, there is still a motion capture suits and stuff like that, but people have developed like you can do capturing using motion capture using cameras and stuff like that. But of course, I mean, you get more accuracy with these motion capture suits still. Of course, gaming is another big thing. Like I said before, in medical visualization, like it's on in this image, you could see. And then, of course, CAD is another thing. And then Google Maps, right? A lot of Google Maps is computer graphics. It uses WebGL or WebGPU in browser to display a lot of, where you can show different. And a lot of these is different kind of complex problems you have to solve, right? It's different. The problem would be, even though the underlying API and underlying fundamental concepts are going to be same, the problem that you will have to solve for visualizing this map on the right hand side versus Jurassic Park movie on the left hand side is two completely different problems to solve. And they will use different algorithms, different ideas, different concepts, even though, but both of them would still need, fundamental understanding of computer graphics APIs and computer graphics in general. Um, so if you wanna basically network with and help with your professional work, I encourage you to attend conferences. Like India also now have game developer conference called something like India GDC or something like that. Game Developer Conference. That would be good. There is a graph here. Usually it happens somewhere in Hong Kong, Australia, or somewhere that I encourage you to go there. There is a CVPR, which is a conference on computer vision, very cool conference, a lot of cool talks, a lot of hand-on workshops. I try to go when I can, but it's a very cool place to be there. You meet a lot of cool people. So yeah, join some professional communities like SIGGRAPH, Computer Society. Try to figure out what's going in Kronos, which is an open standard body that governs a lot of specifications. Look into Reddit, play around with Unreal Engine, Unity, and stuff like that. A lot of people provide guidance. Write your blogs, but try to publish papers in some good computer graphics or computer vision journals. Sometimes you will not succeed, but you will learn a lot in the process. Uh, I'm gonna skip this, but there are devices like a camera like devices like this. It's called OGD, where you can use the devices which gives you depth sensor, and then you can build a lot of cool application. Like for example, here we are almost tracking all the joints and stuff like that. All the things that will require you know some kind of motion capture suit can be now done with the device or a camera like this, right? On the left, on the lower left. Uh, let's considering the time I am it's this is an interesting slide actually, so I'm not going to skip it even though we have a little bit less time. So back in 1950, it's a pretty amazing journey that we have come to if you think about it. And of course, some of you people might not be born even in 1950, including myself, right? I mean, even so, a lot of this thing is very, very cool. Think about this. In 1950, we were able to draw only this oval shape on this screen, with very limited colors that we had. And then there was some kind of vector graphics that we could do. Then there was in 70s we had some CRT, and this is when SIGGRAPH started actually in 1974. We had this Star Wars movie or some kind of Star Wars series, and I haven't watched it at all. But it was a lot of, at that point, they started using some computer graphics to mix with the Star Wars. And if you try to see that, you kind of see it's very limited. You can't really think, see stuff. You can kind of, see it's not real, like not real movies like you get today from Pixar, for example. And in 1980s is when Pixar started. You got movies like Tron, which is pretty, awesome development. And then 90s we have a lot of OpenGL, a lot of graphics, a Terminator movie, Jurassic Park, a lot of cool stuff. And by 2000 we have these movies like Cars, and which are using real time ray tracing, almost, and offline ray tracing. Sorry, not real time ray tracing. So yeah, quite a big evolution, and it's interesting to see how things would evolve in next, let's say, what, 50 years. Yeah, yeah. By 2050, there is a lot of AI gonna come into the picture, and things are gonna change considerably. It's quite possible that we will not be able to tell what is real versus what was, computer generated. It would become impossible. Um, let's see. We have, I would say, I want to take some questions. So I'm going to spend another maybe 5 to 7 minutes before I wrap up, and we will see what we can cover in that. I'm going to skip this, but this is pretty much like an introduction to rasterization pipeline. So I'm going to skip this. This is ray tracing. So I'm going to talk a little bit about ray tracing because, like I said, it's interesting, but this diagram shows it in more detail, right? So think about this eye. You're looking at this image plane. You shoot a ray, but and then it hits an object, and it might miss, and then you get the color of that object. But then there is a from where it hit, it does not ends there. It's going to enter that object. It's going to exit that object, and for each of those, and there is going to be some, like a surface. You can imagine, like you can imagine like a plane where you are going to shoot rays Some of the objects that might be, shadow. Uh, this is some example of global illumination where you are now, having these spheres with your glass spheres, and you will see, some images of how to, if you used a lot of, multiple bounces, you can see, for example, in the lower image versus the upper two images where we don't have all the indirect data, the the sphere bottom part example is totally black because we did not take into the account all the indirect data that was being generated. This is example of global illumination that I was talking about earlier. Uh, this is some idea about ray pipeline, but I'm going to skip it in the interest of time. Uh, so here is an example of rasterization, and again, this has changed considerably. We are able to get this is very old image from some old book or something like that. But you can see from the top upper images and the lower image, in ray trace you get this very crystal clear reflection, while in the upper image you will not get those effects. So in rasterization, even though you will do it in real time, which means like running at a 60 frames per second, it's not going to give you absolute accurate effects at times. And the state of art is not like this. It has changed considerably. This is very old image, but just being presenting it for the comparison purposes. Uh, if you want to be a graphics programmer, you want to learn some of these APIs like Vulkan, WebGL. I think WebGL is kind of now fading away, but DirectX, Vulkan, WebGPU, or Metal is something I recommend learning. I'm gonna. There is another very interesting library called BGFX. Some of these graphics APIs are a little bit hard to learn because they really go low level. And if you are interested in doing like creating stuff, then it might be like, what am I doing? I'm just trying to understand like stuff for the sake of understanding. So it's good to start with some libraries like BGFX, which can help, which can hide these, details, and it can help you, write something that can produce results. So BGFX is such library where you can use it to create like a small engine or small code to do something like produce a shadow, render a 3D object, and without worrying about a lot of details about Vulkan or WebGPU or Metal. I'm gonna skip this. Uh, Again, skip this. This is a tool called Render Doc. Again, I mean, I'm giving very high level overview and trying to cover a lot of things, but so that you guys know about what exists, and then you can go and look into it in more deeply. So a lot of time when you're trying to debug stuff, specifically computer graphics debug stuff, you want some tool so that you can go and say why the color of this pixel is like that, right? Why is it yellow? Why is it green in this case? And there is this tool called Render Doc. So the idea is you run your program, then and there are multiple tools. Render Doc is just one example. There are tools from NVIDIA. There is a tool from Microsoft called Pix, and you can use any tool. It will help you understand what your geometry looks like, what are the different stages of a graphics pipeline, how the things works, and to be able to know what geometry you were rendering and why is the color of certain pixel black, gray, or whatever color, and then you can go and debug your code directly into this. So you basically take a frame, you capture that frame, and then you try to debug it. uh, so let's go into a little bit about stable diffusion. So in a lot of way, computer graphics is being changed by a lot of AI technologies like stable diffusion, 3D content creation. So the idea there is you have a lot of um, you know um, 2D. You have this neural network that has been trained, and you're trying to produce 2D images or 3D content by using this neural network. So stable diffusion or DALI or the things that you have heard about. So the idea is you have a lot of noise, you run it, and then you are able to produce this image from that noise, from the texture. Again, I will not go into detail. I think this is a very common information. There are multiple papers, and I don't think my slides would do justice to those papers. So skip this. But these are some of the examples of what you can do, right, even today. And things have evolved since I created this slide. Actually. So let's do a couple of examples. I can create these 3D objects also from some of those objects that and that's going to be the end of what I have to present. I am happy to take any questions.
Yeah. Thank you, sir, for such an informative session. And let's move forward to questions. Yeah. Okay, so many students feel overwhelmed by the complex tool like Unreal Engine, Vulkan, and USD. So, as a beginner, how can we gradually build confidence in working with like such industry level technologies?
Right. I think that's a good question, and I totally understand. The complexity of these APIs or Unreal or even Unity to certain extent. And I would encourage not to start like if you are a new person into this field, not to start with Unreal or Unity. Even start with building blocks, like trying to build your own engine if that's your goal. And try to use library like BGFX, for example. BGFX is a very thin abstraction over DirectX, Vulkan, or Metal, or any API. So you could technically write in one stream and one code, and then you can run the application on multiple platforms even. And it's easier to program using that API versus using the other option would be using something like WebGL or OpenGL for the learning purposes, because these are still simpler APIs. The idea is to use this as a building blocks, right? One step at a time, get good in that, understand the basics. So, for example, once you learned about how the pipeline works, what are the different stages of the pipeline, how OpenGL works, how I can do this stuff, then you can move to, okay, now I think I understand a little bit more. Let's do Vulkan and try to do what exactly I did in Vulkan, right? Once you understood that, then maybe, okay, can I use Unreal? Okay, but Unreal is very high level. Can I build like a plugin for Unreal where I can control these things through low level, right? Or maybe we don't even need to do Unreal, right? So choosing the right technology, right library is going to be important, and it would of course depends upon what your intent is. If your intent is, for example, to get good in game development, then you will use Unity or Unreal, right? You will not like to use that. But if your intent, like if you want to be a games developer, you don't really want to be graphics developer, then you want to use gaming engines, right? Godot is an example. But if you want to be a graphics developer, then you want to be able to create rendering engine. And then if you want to be, for example, want to become a driver developer, then you want to contribute to projects like Mesa, which is a driver for 3D graphics, or driver basically for stuff. So you want to use some of those low level, but it all depends on interest and where you want to go actually.
Yeah. Okay. Noted. Yeah. Also, like with rendering, like autonomous systems and digital twinning evolving so fast, like what do you think will be the next most in demand skill in the next 5 years for students that are entering this field?
Could you repeat it? I didn't catch it quite close.
Yeah. Okay, so like with rendering autonomous system and twins that are evolving so fast. So, what do you think will be the next most in demand skill in the next 5 years for students who are entering this field?
Yeah, that's going to be a difficult thing to predict, honestly. Like AI is changing things at such a rate, and depending upon how the research changes things, things would be different. I mean, definitely AI seems like a lot of AI technologies, whether it's being used in 3D graphics or general, like, data thing, like general things like, LLMs and stuff like that, is definitely going to be in demand. I would not encourage students to look at in this way what is going to be in demand, but look at the intersection of what looks like would be in some demand. Not like you don't want to target, like, you just don't want to say, okay, figuring out how to train LLM is going to be definitely in very, very high demand. Let's assume that that's going to be there. But then you also have to find whether that do I feel it's interesting or not, right? Like, let's say I found out like computer graphics is gonna be in very high demand, right? But I find it not really interesting to the kind of work that I like to do. And so you want to have to find something that of course have some demand. You don't want to be just like, I want to draw stuff but no one want to buy my painting, but I still want to draw stuff, right? So you don't want to be at the, you want to balance these things. You want to be like, I love to do this thing, but and at the same time there is some market that will consume my stuff. So you want to be able to sell your stuff. Like, think about if you would be someone who would be put in some kind of, experiment, or a real world, hundreds of years ago, and you will have to figure out, I want to do something that I can, you know use to earn something from as well, but also not really feel burdened trying to do that. So you want to find your intersection of your interest areas as well as something that pays whatever your requirements for the getting the paid is. If getting payment and if getting paid is the topmost requirement, definitely AI, LLMs, and those kind of fields are you should go for.
Okay. So we need to find a balance between like what we find interesting and what is like in demand in the next 5 years.
Right. Right. So, for example, I would say like write down like things that are very interesting to you. Start with that. A lot of those ideas, right? Like write down 10 things, and then mark how like, and then maybe talk with multiple people, maybe with people like myself, but other people's post it on LinkedIn. Try to Google, try to figure out what the priority of those things would be, like how much demand of that would be, and then find an intersection where which are those skills that really matches, and that's something you can pick out and then focus on those.
Yeah.
And then it's possible also that you might have to pivot at some point of time. It's like technology changes at different speeds, so it's quite possible you start with today with, let's say, computer graphics, and couple of years when you have graduated you find out the all the jobs for computer graphics that used to be previously done by using creating these rendering engine now can be done better with neural networks. And a lot of these companies are now using that instead of traditional way of rendering stuff, right? Traditional rasterization or ray tracing. Let's assume that in 4 years that gets changed. Yeah, then you're going to have to pivot and learn some of the other skills. So being flexible is also very important in specifically this industry.
Yeah. Okay. So you need to evolve with time, like.
Yeah.
Okay. Yeah. So next question is, like, if a student today wants to get into AR, VR, graphics, or simulation, like, what skills or projects should they focus on to stand out?
Hmm. So I think uh, you said a lot of stuff like AR, VR, autonomous systems. What was
Yeah.
the other thing?
Yeah, AR, VR, graphics, or like simulation. Like, what
Right.
skills or projects should they, yeah, focus on?
So I think it all depends on. I would say if you are if in initially you should try to just build some stuff, right? Like it could be, you could say, okay, I'm gonna build a very small rendering engine to render stuff, and or I'm gonna build this small game using Unity, right? Like as a student, you have a lot of time and not really a pressure to prove that a project is successful. The other cool idea would be to contribute to some open source, and like for example, you could contribute to BGFX and fix their bugs, or they have like a lot of issues created. Like create this example for BGFX. You can try doing that. Uh, you can also contribute to some other projects as per your interest. Open source, contributing to open source really helps you. Now, what projects? It all depends on your area. Like in today's world, I think more than me giving specific answer to a particular AR VR project or idea, you could basically ask these LLMs, and they would give you a lot of cool toy ideas that you can create products from. But I would encourage contributing to some open source. And if you must, or if you choose to create like your own some toy stuff, then try to make it open source, or try to basically you know div- see how you can get it used by other people. Don't do something like where you are just like, I created this thing and I learned it, and I mean, which is fine, which is also not a bad thing, but try at some point, try to create something where you can say, people are using, even if you are not getting money out of it. There are some people, maybe 100 people, maybe 20 people, however many people, those people, like, you are that way you will get like a real requirement. Like, those people will complain to you saying, we want this and that feature, so that will become more like a real time project that you will have to do kind of work.
Yeah, okay. So, like the last question for today, what are some exciting ways that AI is changing the future of rendering or like graphics?
Uh, right. So, like I said in my presentation, a lot of neural techniques like NERF, neural radiance fields, Gaussian splats, if you look it up, these are different ways of rendering, 3D scenes or 3D data at the end of the day. 3D data used to traditionally be represented using, vertices, faces, triangles, and stuff like that. But now with these things like a neural network or Gaussian splats, which is a different way of representing things trained using neural networks, things are changing. So this is one example. Then there is a techniques like upsamplers, like DLSS, which is from NVIDIA's deep learning super sampling techniques, where you can render at, let's say, 1080 resolution, and then upscale it to 4K resolution, and that way your video game, and it looks in a video game as if it was rendered at a 4K resolution, basically. So that means a lot of time that was, and the idea is you are converting, going from a 1080p to 4K in less time than it will take to actually render a 4K image. So so yeah, so those are the kind of the techniques, and these are areas are evolving. There's a lot of, like, there is things like a neural texture compression, for example, how to compress data better. Like, that's a generic thing, but how to compress in case of, so for example, GPU memory is limited. A lot of, when you upload data to GPU, a lot of time you want to compress your data, and there are traditional analytical techniques to use to compress data that are currently being used. For example, you would say, like, like a very simple example would be, let's say if you have a string, and I could, like, instead of storing the full string, I could maybe store some kind of count of character, or some kind of, offset indexes, some kind of way, right? Like, and so there are multiple ways of, that's a very small example, but yeah. So, but with neural network, what you would be doing is you will take this and you will be able to compress it, which is commonly called like a latent space, where you now have a very small, set of layers and things that basically you have compressed your data, and then from there, when you are gonna run that MLP on your GPU, you could be able to infer the data. Now, it might not absolutely be as accurate as, but if it's even 99% accurate or 90% accurate, it might be good enough for some scenarios.
Yeah. Yeah. Okay. So, with that, like, thank you for joining us, and that was an amazing journey into the worlds of graphic and AI, like with you. And thank you for sharing your expertise and passion so generously. Like, I hope this session sparked new ideas and gave everyone a fresh perspective on exciting innovation in the space. Yeah, also, like, don't forget to follow Pritish for more insights and stay connected with the community. Yeah, thank you to all of you for your enthusiastic participation. Like, let's give a round of applause for Pritish Kakkar. See you next time. Thank you,
Thank
sir,
you.
for joining us. Yeah,
Thank you. Bye.
bye.